Welcome to AI Patent Watch, the podcast where we break down an exciting AI patent in each episode, what it covers, why it matters, and how it's impacting innovation. Whether you're a patent professional, an AI enthusiast, or an inventor looking for inspiration, you're in the right place. Let's dive into today's AI patent.
Welcome to the Deep Dive. Today we're tackling a challenge that's fundamental to all sorts of systems that need to see and understand the world. Think self-driving cars, security cameras.
Robots navigating factories, that kind of thing.
Exactly. And the challenge, keeping track of objects when they, disappear from sight. It's called occlusion. Exactly.
And we're diving into some pretty fascinating source material here, specifically excerpts from a recent European patent, EP4 488-939B1.
Okay.
And this patent, it describes a really quite clever computer-implemented method designed specifically to improve object tracking, especially when things get hidden.
Right. So in this deep dive, our mission for you listening is to really unpack the problem of occlusion. We'll look at how tracking systems usually try to cope when an object vanishes.
Understand the limitations of those sort of traditional methods.
Yeah, and they get into how this patented invention proposes, a smarter way forward by mapping out the scene's blind spots, essentially.
Object tracking really is a core task in computer vision. It's all about continuously identifying, locating objects within a stream of sensor data.
Could be video, could be radar, LiDAR, whatever the system's using for eyes, basically.
Right. And the big hurdle, as you said, is occlusion. Simple idea, really.
Yeah, the object you're tracking is there. Then it's not. Something's blocking the view.
Like a car behind a bus, the source mentions, or a person walking behind a tree or a building.
Right. So when that happens, the system loses the track. It just doesn't see the object directly anymore. What then?
Well, what does it do? A common first try is something called coasting.
Coasting. Okay.
The system basically makes an educated guess. It takes the object's last known movement, its speed, its direction, and just extrapolates, predicts where it might be.
You know, like trying to follow someone behind a wall just by guessing based on how fast they were walking before they went behind it. The patent shows this as a hypothetical track.
But the limitation, and it's a big one, is that this prediction is only good for so long. If the object changes speed or turns or anything while it's hidden,
that hypothetical track goes wrong pretty fast.
Exactly. The error just builds up the longer it's hidden.
And there's usually a time limit, right? A coasting period.
Yep. A fixed time. If the object doesn't pop out again and get detected within that window,
the system just gives up.
Yeah.
Track lost permanently. The figures show that too.
So if coasting doesn't work out, or maybe instead of it, systems might try re-identification, re-ID.
Okay, that sounds more involved.
It is. It's more complex. So when new objects suddenly appear, maybe near where that track was lost,
the system tries to figure out, hey, is that the same guy I lost track of?
Pretty much. It involves extracting what the patent calls meaningful features from these new detections.
Meaningful features? Like what, for video?
For video, yeah. It could be color patterns, shape information, texture, basically creating a sort of numerical fingerprint for the object.
Yeah.
Then it compares that fingerprint to the one it remembers for the lost object. Using similarity measures like how mathematically alike are these two objects, and more advanced stuff uses deep learning, CNNs, convolutional neural networks. They're really good at finding complex visual patterns for this kind of matching.
But that sounds computationally heavy. Lots of processing.
It absolutely can be. And another major limitation here, re-identification often really leans on visual features.
So if you're using radar or LiDAR.
Exactly. They give you distance, speed, but not the visual appearance like a camera does. So these typical re-ID methods based on how things look often just aren't possible. You can't use them.
Okay, so we've got coasting, simple, guess-based, limited time, prone to error.
Right.
And re-identification, smarter for visual data, but needs lots of computing power and doesn't work for all sensor types.
Correct.
Feels like there's a gap. The system doesn't really learn about the blind spots themselves or how objects tend to move through them.
That's exactly the point the source material makes. It says, maybe you could maintain a map of occluded areas, but figuring out where those areas are accurately and then using that map effectively to predict what happens inside them, that's been the tricky part.
There was a clear need for something better.
Definitely. Which brings us to this patent, EP4 488-939B1, and it's got a really neat core idea.
Okay, let's hear it.
It's a computer-implemented method, and it figures out where the occluded areas are. but not by looking at like static walls or trees.
How then?
It learns from the objects themselves. Specifically, it leverages successful re-identifications.
So when the system does manage to find a lost object again.
Exactly. That successful re-ID is valuable data. If you lose an object here and successfully re-identify it over there...
That tells you it must have traveled between those 2 points while hidden.
Precisely. You're using the successful journeys to kind of reverse engineer the map of the blind spots. Where they start, where they end.
That's clever. So it builds a map of one or more occluded areas.
Right, and this map isn't necessarily a visual map. Think of it more like a database of connections.
Connections between
locations where tracks tend to get lost.
Yeah.
And locations where those same objects tend to reappear later.
Okay, so how does it build this map step by step?
Right, so you feed it video sequences, it tracks objects, standard stuff.
Okay.
Then, let's say a track gets lost. Maybe no detection, or maybe coasting failed. The system runs its re-identification algorithm, trying to find that object again among any newly detected, untracked things.
And the key is if it succeeds.
Exactly. If re-identification works, the system notes two things. The area where the track was lost, let's call it the start area.
Got it.
And the area where it was successfully re-identified, the end area.
And these areas are like regions in the scene.
Yeah, representations of 3D space in the 2D video, maybe using some base coordinate system. The patent mentions this.
Okay, so it identifies the start area and the end area for a successful re-ID.
And then it adds a connection between that start area and that end area to its map.
Like drawing a line in its database. Object lost here, reappeared there.
Exactly like that. And it does this over and over again for lots of different lost tracks that get successfully re-identified.
So the map gets built up from the collective experience of all the objects moving through the scene. It learns from the crowd.
That's a good way to put it. It learns from the crowd. And the map can show, for instance, that from one start area, say, behind a big pillar,
objects might reappear in multiple different end areas. Maybe they go left, maybe they go right.
Precisely. And even cooler, the map can optionally store the probability for each connection.
Based on how often each path is taken.
Yeah. If, historically, 80% of objects lost behind that pillar reappear on the left and 20% on the right, the map records those likelihoods.
That adds another layer of intelligence. What about the areas themselves? Are they predefined?
They can be. You could manually define regions around known obstacles, like drawing boxes. But the patent also describes a more adaptive way. The system can look at all the locations where tracks were lost and all the locations where they were resumed.
And automatically group them, cluster them.
Exactly. It dynamically figures out the significant start and end zones by clustering these points. Figure 4 in the patent actually illustrates this idea.
So it adapts to the specific scene automatically. It's quite elegant.
It really is. It takes the results of something the system often does anyway, re-identification, and turns that outcome into structural knowledge about the scene's blind spots.
Without needing extra sensors just for mapping or lots of manual setup. It's data-driven, learning from behavior.
Which is a powerful approach. And, developing and crucially patenting these kinds of sophisticated computer-implemented methods, it's not trivial.
Especially with AI components like potentially deep learning for that re-ID.
Absolutely. You need deep technical understanding, of course, but you also really need to grasp the nuances of patent law for software and AI inventions, defining what's truly novel and inventive.
It requires specific expertise.
It really does. That's why having an experienced European patent attorney who specializes specifically in this intersection of AI, software, and patent law, someone like yourself, Bastian Best, is so critical for companies developing these advanced technologies. Getting that protection right, especially in Europe, needs that focused skill set.
It's definitely a specialized field where technology and law meet very closely.
Wrongly.
Okay, so the map is built maybe offline first, or maybe it keeps learning online. How does it actually help in real-time tracking?
Right. How do we use it? Well, it makes the tracking much smarter when an object does disappear. Let's take coasting first.
Okay, so a new object, let's call it the second object, is being tracked live.
Yep, and boom, it goes behind something untrackable.
The system knows its last position.
Right, it checks.
Yeah.
Is this last known position near one of the start areas recorded in our map?
And if it is,
the map gives it intel. It says, okay, objects lost here usually reappear over there, pointing to a mapped end area.
And if there are multiple possible end areas from that start area,
it can use those probabilities we talked about. Pick the end area that's historically the most likely outcome.
Okay, so it knows the likely start and end points of the hitter path. What good does that do for coasting?
This is the key improvement. It allows the system to estimate the typical distance or travel time through that specific blind spot.
By measuring between the map start and end areas.
Exactly. And then here's the clever bit. It sets the coasting period for this specific track based on that estimated distance or duration.
So no more fixed one-size-fits-all coasting time.
Nope, it's adaptive. If the map indicates a long path through this particular occlusion,
the system will coast for longer, giving the object more time to reappear before giving up.
Precisely. It tailors the coasting to the scene's actual structure and learned object behavior. This massively increases the chance of reacquiring the object smoothly when it emerges.
And it reduces the need to fall back on that expensive re-identification process later.
Absolutely. And think about those sensors like radar or LiDAR.
Where re-ID isn't really an option.
Right. They can still benefit hugely from this smarter, map-informed coasting. The map might have been built using camera data, but the improved coasting logic helps the radar track persist longer and more accurately through occlusions.
It could also work the other way, right? If the map shows a very short, known occlusion.
It could set a shorter coasting period, allows it to drop a bad hypothetical track quicker if the object doesn't reappear fast, avoiding too much error buildup.
Makes sense. Can it be even more refined?
Yes. The patent mentions refining the coasting period further by considering the object's speed just before it vanishes.
Oh, right. A faster object covers the same distance quicker.
So for the same estimated path length, a faster object might get a slightly shorter coasting time allowance.
And what about the prediction during coasting? Can the map help there too?
It can. Beyond just using the object's last speed, the map itself might hold clues about the typical path or angle taken between a start and end area.
So not just the endpoints, but maybe the shape of the path between them. Learn from past tracks.
Potentially, yes. The system could use this historical trajectory information from the map to guide the hypothetical track it maintains while the object is hidden, making the prediction itself more informed.
Using the collective wisdom from the map to make a better guess about where the object is right now. Very smart.
Oh.
Okay, that's coasting. What about re-identification? How does the map help there?
It helps optimize the preparation for re-ID. Remember, we said feature extraction for re-ID is computationally demanding.
Yeah, you don't want to be doing that constantly for every little blip that appears.
Exactly. You want to be strategic. So imagine a third object is being tracked, and the system sees it heading towards a start area that's marked on the map.
It's approaching a known blind spot.
Right. The system can anticipate, this object is likely to get occluded soon.
So it gets ready?
Precisely. Knowing it's likely to enter that occlusion zone, the system can proactively prioritize calculating its feature vector, its fingerprint, before it disappears.
So it does the heavy lifting before the crisis hits.
Exactly. That way, if the object does get lost and needs re-identification later when something pops out near the expected end area, the system already has that crucial feature vector ready for comparison.
That saves a lot of computation compared to trying to extract features from memory or from the last good frame after it's already gone.
It's about resource management. Using the map's predictive power to allocate computational effort more effectively.
That's a really clever optimization. Using the map not just reactively, but proactively.
And the source material briefly touches on other potential uses, too.
Oh, yeah. Like what?
Well, think about privacy masks in video. Maybe the map could inform where those are needed or less critical. Or video compression, perhaps you compress areas where objects are predicted to reappear less to make sure you capture them clearly.
Interesting.
Or even adjusting sensor processing, things like noise filtering, image game, tone mapping, tweaking them specifically in the zones where the map predicts an object is about to emerge from hiding.
To maximize the chance of a clean detection as soon as it reappears.
Could be, yeah. Lots of potential downstream applications once you have this map.
Okay, so let's pull this all together. This deep dive into EP4 488939B1, it really shows a powerful shift, doesn't it?
I think so. Using the results of successful re-identifications, learning from past reappearances, to build this dynamic, data-driven map of occlusions.
And this map isn't just a picture, it's a tool. It makes the whole tracking process smarter, more efficient in real time.
Definitely. By understanding those historical connections disappear here, reappear there, the system can tailor its response.
Setting better adaptive coasting periods, predicting paths more accurately inside blind spots.
And even optimizing demanding tasks like getting ready for re-identification by focusing its efforts where they're most likely needed.
It really tackles those key limitations of older methods, grounding predictions in actual data learned from the specific scene.
Which not only boosts accuracy, but significantly helps bridge the gap for sensors like radar and LiDAR, extending better occlusion handling to them too.
It's a really solid step forward. So here's something for you to think about after this. We've seen how historical re-identification data can map occlusions. But what else could we learn from the vast history of tracked object data? Think about typical movements, interactions, behaviors in different contexts. How else might we leverage all that past data beyond just occlusion mapping to predict future actions in a really supercharged tracking performance in complex, unpredictable environments?
And that's a wrap for this episode of AI Patent Watch. If you found this helpful, please take a moment to leave a 5-star rating and subscribe so you don't miss future episodes. This podcast is curated by Bastian Best, a European patent attorney specializing in AI patents. To learn more about the exciting intersection of patents and AI, sign up for his mailing list for exclusive insights. Link in the show notes. And if you're already working on the next big AI innovation, now's the time to secure your own patent. Reach out to Bastian on LinkedIn or the podcast website to turn your ideas into assets. Thanks for listening, and stay tuned for the next episode of AI Patent Watch.